Let's take a look at a graph and see if we can do some limits using what we've learned about left and right limits and figuring out when limits exist. So consider the graph of f of x below. This is called a piecewise function because this is defined by different functions for different parts of the graph. We can see that there's some holes and some jumps, so we're going to have to be really careful with our limits. There's three limits that we want to compute here. The first one is the limit as x goes to 1 of f of x. So as we approach 1, we're considering what happens to these functions. So we're going to start by seeing what happens as we approach 1 from the right. So something to the right of 1, that means we're defined by this function up here, this line. So as we approach 1 from the right, the y value that we're approaching is 3. So again, since we never actually plug in 1, we're asking what happens when we get close to 1 from the right. As we get close to 1 from the right, we get close to 3. Now, when we consider what happens as we approach 1 from the left, we're on this sort of U-shaped function. So here as we approach 1 from the left, we're approaching a y value of 1. So here, the limit from the right exists, the limit from the left exists, but they're different, which means that the limit itself, the limit as x goes to 1 of f of x, does not exist because it's different when you approach it from the left and the right. Now let's consider what happens as we approach negative 1. So as we approach negative 1, again, we're going to consider what happens from the right and the left. So let's start by looking at what happens when we approach from the right. So that means we're starting with values a little bit to the right of negative 1. So as we approach negative 1 from the right, the y value that we're approaching is positive 1. Similarly, when we approach negative 1 from the left, we are also approaching a y value of 1. So here, the limits from the left and the right both exist, and they're the same. If they're the same, that means the limit itself exists and the limit equals 1 because that's what the limit from the left and the right both equaled. So here at negative 1, our limit exists. Now, finally, let's look at the limit as x approaches 2. So again, we're going to consider what happens from the left and the right. So the limit as x approaches 2 from the right of f of x means that we're on this upward sloping line here, and we're considering what happens as we get close to 2 as we're coming down from the right. So we can see that the y value as we approach 2 from the right is going to be 2. If we look at the limit as x approaches 2 from the left, however, now we're on this horizontal line. So as we approach from the left, the y value that we are approaching is 3. So again, the limit from the right exists and the limit from the left exists, but since they're not the same, that means the limit itself as x goes to 2 does not exist. So when you're considering whether or not limits exist, you need to be looking at what's happening from the left and the right to figure out if the limit itself exists. While we can always use charts to plug in and get close to numbers with algebraic formulas to see what the limit is, sometimes it's useful to try to simplify what we're looking at the limit of before we take the limit. So for example, consider the limit as h goes to 0 of 2 plus h squared minus 4 all divided by h. So this is another case where if we had tried to plug in h equals 0, we'd end up with a 0 in the denominator and numerator, and that wouldn't be so good for us. So we know that we want to make a chart, and we want to see what happens as h gets close to 0 from the left or the right. But what we can do here is we want to first see if we can use algebra to simplify the expression. So the limit part stays the same. We're still taking the limit as h goes to 0, but now in the top, I'm going to square out the 2 plus h squared term. When I square that out, I'm going to get 4 plus 4h plus h squared. And then I have a minus 4. And that's still all divided by h. Now, combining like terms, I can look at these constants. So notice I have a 4 in the first term and a minus 4 at the end. So I can cancel those out, and I'm left with a 4h plus h squared over h. And what I can do here is I can factor out an h, so the limit as h goes to 0. So on the top, if I factor out an h, I'm left with a 4 plus h divided by h. And the reason why I wanted to factor out that h is so I could cancel it with the h on the bottom. So now I have the limit as h goes to 0 of 4 plus h. So this is a simpler function to work with, and I have a pretty good intuitive idea of what this limit is going to be. So again, I need to consider what happens as I pick my h values close to 0. So again, from the right, I will pick 0.1, 0.01, and 0.001. And then my function, 4 plus h, that's going to give me 4.1, 4.01, 4.001. And I feel comfortable saying that that's approaching 4. When I consider what happens as I approach 0 from the left, so again, I'm on the negative side of 0 on that number line, I'll have negative 0.1, negative 0.01, negative 0.001. When I plug that into 4 plus h, I'm going to get 3.9, 3.99, 3.999. So now I have the limit as h approaches 0 from the right is 4. And I have the limit as h approaches 0 from the left is 4. So therefore, the limit of the whole thing is going to equal 4. I want to point out that here we use the variable h instead of x. It doesn't matter what your variable is because you always assume that whatever the variable is under the limit is your independent variable, and you plug everything in the same way. So again, the point of this example is that sometimes it's easier to simplify your function first before you take limits to do your calculations. And we'll see why that might become powerful in the next section. So finally, we want to have a good intuition about looking at a graph and determining where the limit is not going to exist. So you can see that at the points where the function is continuous, the limit is going to exist because we're always going to be approaching the same y value from the left and the right. The points where we get concerned are the points where our function is jumping or has what's called discontinuities. We're going to talk more in depth about this in the next section. But here, where our graph doesn't seem to continue in a nice even flow, are the points where we're really concerned about the limits. So here, my limit's not going to exist when x equals -1, because again, the limit from the left is going to be 0, and the limit from the right is going to be 1. So those are different. And then it's also not going to exist at x equals +1. So at +1, the limit from the left is going to be 1, and the limit from the right is going to be 2. And those limits are different, so the limit does not exist. And there's even another awkward point here because the actual value at 1 is -2, and neither of those limits even come close to the actual value. So when we have piecewise functions, we're always concerned at the points where our function takes on a new part of the graph. So when you look at these types of pictures, you can identify where this limit's not going to exist by finding these discontinuities.